Welcome to this mathematics and hydrology tutorial. Today, we'll be solving a problem about calculating the depth of excess rainfall from a hydrograph. A hydrograph shows how water discharge in a stream changes over time, and understanding it is crucial for water resource management and flood prediction. Let's look at the problem. We're given a hydrograph that shows the discharge measurement in liters per second at various times for a watershed that has an area of 12 square kilometers. Here's the data table showing the measurements every 3 hours. The problem also states that the base flow is practically close to 200 liters per second. Base flow is the normal background flow in the stream without any rainfall contribution. We need to find the depth of excess rainfall, and we're given 4 options. A 15.4 millimeters, B 12.8 millimeters, C 10.2 millimeters, D 8.4 millimeters. Let's solve this step by step. Step 1. We need to subtract the base flow from each discharge measurement to find the excess flow. Let's define Q sub B as the base flow, which equals 200 liters per second. For each observed discharge Q sub I, the excess Q sub E comma I is equal to Q sub I minus 200 liters per second. Let's create a table with the excess discharge values. Before we continue with the calculations, let me visualize the hydrograph for you. The blue line shows the total discharge over time, and the red area represents the excess flow above the base flow, which is what we're concerned with. The base flow is shown as the constant green line at 200 liters per second. Our goal is to find the total volume of water represented by the red area, and then convert it to an equivalent depth of rainfall over the entire watershed. Step 2. Now we need to calculate the total volume of excess water. To do this, we'll use the trapezoidal rule for integration. Since our data points are at regular time intervals, this is an appropriate method. The readings are taken every 3 hours, which is 10,800 seconds. We have 15 data points, meaning 14 intervals between them. For each interval, the contribution to the volume is calculated as the average of the 2 excess discharge values multiplied by the time interval and converted to cubic meters. The formula for the volume contribution of each interval is V sub I equals the average of Q sub E comma I and Q sub E comma I plus 1 multiplied by 10,800 seconds, and then multiplied by 10 to the negative 3 to convert from liters to cubic meters. So our total volume is the sum of all these interval contributions. V equals the sum from I equals 1 to 14 of V sub I, which equals the sum from I equals 1 to 14 of Q sub I minus 200 plus Q sub I plus 1 minus 200 divided by 2, multiplied by 10,800, and then by 10 to the negative 3. To make our calculation easier, we can simplify the formula a bit. We can rewrite it as the sum of Q sub I plus Q sub I plus 1 minus 400, all divided by 2, and then multiplied by 10,800 times 10 to the negative 3. When we add up all the discharge values following this formula, we get a sum of 28,110. Plugging this into our equation, V equals 28,110 divided by 2, multiplied by 10,800 times 10 to the negative 3, which gives us approximately 151,800 cubic meters. Step 3. Now, we need to convert this volume of water to an equivalent depth of rainfall over the entire watershed. The watershed area is given as 12 square kilometers, which equals 12 million square meters. To find the depth, we divide the volume by the area. Depth equals volume divided by area, which is 151,800 cubic meters divided by 12 million square meters, which equals approximately 0.01265 meters. Converting to millimeters, we get 12.65 millimeters. Looking at our answer options, the closest value is 12.8 millimeters, which is option B. So, to summarize what we did, first we subtracted the base flow from each discharge measurement to find the excess flow. Second, we used the trapezoidal rule to calculate the total volume of excess water, which came out to approximately 151,800 cubic meters. Third, we converted this volume to a depth by dividing by the watershed area, giving us approximately 12.65 millimeters. Therefore, the answer is option B, 12.8 millimeters. This calculation has important practical applications. The depth of excess rainfall helps water resource engineers understand how much water will run off during a storm event. This is crucial for designing drainage systems, flood control measures, and water management strategies. Thank you for watching. I hope this explanation helped you understand how to calculate the depth of excess rainfall from a hydrograph.